Hello, today we're going to review for the AP Chemistry exam by going over the free response from 2018. We'll start out with question 1, which is a long free response question. It's worth 10 points total. Okay, so we've got this oxidation reduction reaction above, and we're trying to determine the enthalpy change. For part A, we want to determine the oxidation number of chlorine in this compound. So oxygen in compounds is always -2 unless it's a peroxide, which this is not a peroxide. So -2. The sodium here, it's a metal ion, so it will have the same oxidation number as its charge, which is +1. And so then to get this all to balance, the chlorine must also be +1, so it all adds up to 0. So chlorine is a +1 oxidation state. Now, calculate the number of grams of this Na2S2O3 needed to prepare 100 milliliters of 0.5 molar. Big one to remember is molarity times liters gives you moles. That one's used all the time, so it's worth remembering. Molarity is 0.5, our liters is 0.1, so 0.05 moles is needed. And then you would use the molar mass of the Na2S2O3, which is 158.10 grams per mole for the molar mass for that substance. So then you would, that would cancel and you multiply, you get 7.90 grams. And it looks like we're using 3 sig figs here because of the 3 in molarity. Okay, so in the experiment, we're using these concentrations of our reactants and this volume of each of the reactants, same for all 3. Using the balanced equation, determine which reactant is a limiting reactant and justify your answer. So if you have the same molarity and the same volume, they're all going to have the same moles. So you needed to indicate that. But if you have the same moles, you're going to use up the NaOCl fastest because you use up 4 of them every time the reaction happens. So NaOCl is your limiting reactant because you use up 4 for each reaction compared to only 1 or 2 for the other things. Okay, so then you combine them in an insulated calorimeter. The temperature of the reaction mixture is monitored as shown in the graph below. According to the graph, what is the temperature change of the reaction mixture? So you really just need to subtract, but you want to try to use correct significant figures. So right here, we're at just about 32.5, and you started at 20. And so when you subtract, it's 12.5 degrees Celsius is my change. Okay, so the mass of the reaction mixture in the calorimeter is 15.21 grams. Calculate the heat energy in joules that is released. So notice it says magnitude, so you don't need to worry about the sign, but it does say it's released, so we know it's an exothermic. And then they give us the specific heat. So we need to use Q equals MC delta T. The mass of the mixture is 15.21. Our specific heat of the mixture is 3.94, and we just found our change in temperature was 12.5. Now, if you got the previous question wrong, but you used it correctly here, you could still get the points. Just make sure you're showing your work and the formula that you're using. And when you multiply those, you get 749 joules. Then it says, using the balanced equation for the oxidation reduction reaction and your answer to part C, calculate the value of the enthalpy change of the reaction in kilojoules per mole reaction and include the appropriate algebraic sign with your answer. So the important part here was that we determined that NaOCl was our limiting reactant. So we need to use what we know about the NaOCl to help us calculate. Now, in the data table on the previous slide, they gave us, it was 0.5 molar concentration and 5 milliliters, so 0.005 liters. So that means I have 0.0025 moles of that substance. So now what I want to do is find the moles of reaction, 0.0025 moles of the NaOCl. Cl. And I know that there are 4 of the NaOCls used for every 1 reaction. So if I divide that by 4, I get the moles for the reaction, which is 6.25 times 10 to the negative 4th moles of reaction. Now I can change the joules we found in part I here to kilojoules, so 0.749 kilojoules, and divide by the moles of reaction. And that way we'll get the correct units for our delta H that we're looking for, kilojoules per mole reaction, which we get, let's see, we can get 1.2 times 10 to the 3rd kilojoules per mole reaction. You didn't have to put it in scientific notation. But what you do need to do is look back to part I, because part I told you that it was released. And for part II, it doesn't say magnitude. So we do need to pay attention to this sign. So the value of the enthalpy change here needs to be negative because it's an exothermic reaction. It's releasing energy. So you need to have that negative sign as well. This was an involved question. And again, if you didn't want to put it in scientific notation, that was okay. Negative 1200 kilojoules per mole reaction. Okay, the student repeats the experiment, this time doubling the volume of each of the reactants as shown in the table below. The magnitude of the enthalpy change calculated from the results of the second experiment is the same as the result calculated in part EII, and explain this result. So it is the same. Well, that makes sense because you're dividing by the moles of reaction. So the Q, if you were to solve for Q, the Q would be much larger. But the moles of your reaction is also much larger. So because both of those are larger, you're going to have the same ratio, kilojoules per mole reaction, which is why you get the same value for the enthalpy change. And then for the last part, we needed to write the balanced ionic equation. Let me rewrite the equation that they gave us in the problem. Na2S2O3 aqueous plus 4 NaOCl aqueous plus 2 NaOH aqueous yields to, I'm going to run out of space, Na2SO4 aqueous plus 4 NaCl aqueous and H2O liquid. Okay, so anything that winds up being aqueous on both sides winds up being a spectator ion. So let's see, it looks like our sodium ions, and we've got a lot of them, so we have 8 sodium ions on either side. So all of those sodium ions are all aqueous, like that. But it looks like everything else changes partners, so they're not going to be the same. So let's go ahead and rewrite just the things. So S2O3 negative. It's actually 2 negative because there were 2 sodiums attached to it. And we have our OCl negative. And we have our OH negative. And on the product side, we have sulfate, which is 2 negative. And I forgot my coefficients, of course. So this is 4, and this is 2. And there's 2 sulfates as well. Coefficients are important. Make sure you use them. And then we have 4 chlorides and water. And then there's our states. And so that is your net ionic equation, which I didn't do the most neat version of this, but you want to make sure you include the coefficients, include the correct charges. Anything that's aqueous splits apart, anything that's the same on both sides gets canceled out as a spectator ion. So now let's look at question 2, the second long phase response question. Okay, so we have a reaction here with a bunch of gases, and they give us the particle level representation at the completion of the reaction, so the products. And in the box on the left, they want you to draw the particle level representation of the reactant mixture. Okay, so let's look at this. We have 4 of the NO2s present and we have 4 of the NOs present. Okay, so these are the new things. Okay, the 4NO did not change. So I'm going to go ahead and just redraw those 4NO molecules. Okay, so because those did not change in the reaction, but I produced 4NO2, so that means I must have done this overall reaction twice in order for that to happen. So if I do this twice, I have another 4 NO2 molecules. 1, 2, 3, 4, and 2 O2 molecules, like that. And so now everything is stoichiometrically equivalent to make sure that we have those products being formed. Now the NO and NO2 will react as shown, and they give us thermodynamic data, so our delta H, delta S, and delta G. Notice delta S is in the wrong unit there. Okay. That's a common occurrence. They usually give it to you in joules. You typically will need to change that into kilojoules. So for part I, we want to calculate the value of the equilibrium constant K for the reaction. And to do that, we need to use the delta G value. So our equation delta G equals negative RT ln K. Our delta G is, we need to put that in joules for this equation. So 870 joules. Our R is 8.314. Temperature is 298. And then ln K. Do 870 divided by negative 8.34 divided by 298. And then do E to that answer to get your value for K. And you get that K is equal to 0.70. And there's no units for K because it's a ratio of products to reactants. Okay, so now if both of the pressure of the NO and pressure of NO2 in the vessel are initially 1, will the pressure of N2O3 at equilibrium be equal to 1 and justify your answer? So you could use an ice chart here if you want to take a look at that. Okay, so they told us we're initially at 1 and we don't have any of this stuff to begin with. This will go down by x, and up by x. 1 minus x, 1 minus x, and x. And so if I were to use the equilibrium expression, I know that K is equal to 0.7, and then it's products over reactants, so x over 1 minus x squared. Well, I know it's not going to be 1. So if x were 1, then I would completely use up my reactant molecules, and then I'd have 0 on the bottom, which would make this undefined and not equal to 0.7. So you would say, no, the pressure of the N2O3 is not equal to 1, because the value of K is 0.7, and we need to make sure that there's still products and reactants in that ratio present. So there's no way it could be exactly 1. And you can use the ice chart to help in your explanation if you choose. Okay, for part C, student hypothesized that increasing the temperature will increase the amount of N2O3 in the equilibrium mixture and indicate whether you agree or disagree and justify changing the temperature on an equilibrium system. This is Le Chatelier's principle. So this is a negative delta H, so it's exothermic. So we imagine the heat is being released as a product. If I increase the temperature, it wants to move away from the heat, so it will create more reactants. So it says, the student hypothesized that increasing temperature will increase the amount of N2O3. You should disagree because according to Le Chatelier's principle, increasing the temperature of an exothermic reaction will shift the reaction towards the reactants, which would decrease the amount of N2O3. Now that N2O3 molecule reacts with water to form nitrous acid, involved in the production of acid rain, and the skeletal structure of the HNO2 molecule is shown in the box below. Complete the Lewis electron dot diagram of the HNO2 molecule, including any lone pairs. That was nice of them to remind you. Okay, so hydrogen has 1 valence electron, oxygen has 6 valence electrons, and nitrogen has 5. So we know nitrogen has 1 lone pair, oxygen has 2 lone pairs for both of those. So you don't want to forget those. Oxygen tends to form 2 bonds, so we know that it's going to form 2 bonds like that, and then 2 bonds here, which makes sense for nitrogen as well, because nitrogen likes to form 3 bonds. And that way all of the octets are satisfied. Especially considering all of these are in the first or second periods on the periodic table, they do not want to expand their octet at all. So we need to be very careful with that. All right, now based on our completed diagram, identify the hybridization of the nitrogen atom in the HNO2 molecule. So the nitrogen atom has 3 areas of electron density around it: the lone pair, the double bond, and the single bond. So 3 areas, that's sp2 hybridized. Think about it this way: an S and 2 Ps, that's 3 areas of bonding, or 3 areas of electron rather. So sp2 hybridized. You don't need to explain anything here, you just need to write out sp2 and you're done. Now if you drew it wrong in part I and your nitrogen was different, you could still earn the points for II. You need to make sure that they do match though, especially because it says based on your completed diagram above. So be careful with that. Okay, so now the student bubbles N2O3 into distilled water. Assume the reaction goes to completion, then that HNO2 is the only species produced. To determine the concentration of HNO2 in the resulting solution, they titrate a 100 milliliter sample with 0.1 molar KOH, and the neutralization reaction is represented below. Cool. And then they give us the titration curve and the change of pH. Determine the initial concentration of the HNO2 solution. So whenever we're finding concentration, we want to use the volume at equivalence point. So I have 0.02 liters, right, liters, times the 0.1 molar concentration will give us 0.002 moles of the KOH. And we know it's a 1-to-1 reaction there, so I also know I have 0.002 moles of HNO2. And I can divide by the original total volume in liters, so 0.1 liters, which gives me a 0.02 molar concentration for part I. And then for part II, to estimate the pKa value, you want to use the half equivalence point. So if our equivalence point is 20, half equivalence point is at 10. We know it's over 3, so then you can estimate for part II. So let's say it's maybe 3.3 or 3.4. I know it's between 3 and 4, so I can kind of estimate. Let me look at the scoring guidelines. I'll give you the range that they said was acceptable. They said it's about 3.4, but as long as it's, in an acceptable range, you're good. When it says to estimate, don't give a range, like pick a specific value in that range. And then for part F, during the titration, after a volume of 15 milliliters has been added, so now we're here, right? Which species, HNO2 or NO2 minus, is present at a higher concentration, and justify. So at half equivalence point, your weak acid is equal to your conjugate base right here. Before that point, the pH is lower, so you'd have more of the acid. Past that point, but before equivalence point, you're going to have more of the conjugate base. So for F here, you would say NO2 negative is present at a higher concentration because it's past the half equivalence point. And the pH is higher than it is at the half equivalence point, or higher than the pKa, indicating that you have more of the conjugate base present. So now let's look at question 3. This is the last of the long free response questions. Okay, so we're looking at iron and 2 of its ions. Write the ground state electron configuration of the iron 2+ ion. So for this, we know that iron normally has 26 electrons. To cancel out, it's 26 protons, 26. So then the iron 2+ ion will have 24 electrons. So it's going to use, we start at 1s, so 1s2, 2s2, 2p6, 3s2, 3p6. And then because it's losing those 2 electrons and it's a transition metal, it's likely to steal the electrons from the 4d sublevel to keep its 3d sublevel half full. So that means instead of going straight to 4s, we're going to skip over to 3d and fill in those last 6 electrons. So that is a little bit more stable than having the 4s and then the 3d. So that would be the electron configuration there. And then they give you the ionic radius for 2 of the ions. Explain why the radius of the Fe2 plus ion is larger than the radius of the Fe3 plus ion. So this has to do with Coulomb's law. They both have 26 protons, but iron 2 plus has 24 electrons and 3 plus has 23 electrons. So the protons exhibit a greater force of attraction per electron, pulling them in tighter and making that radius smaller compared to each of the electrons in the iron 2 plus ion has relatively less attraction to those 26 protons, giving it the larger radius. Now for part C, the iron 3 plus ions interact more strongly with water molecules than the iron 2 plus ions do. Give one reason for the stronger interaction and justify your answer using Coulomb's law. Coulomb's law, remember, is based off of 2 things, charge and distance. So a higher charge and a smaller distance will indicate stronger Coulombic attractions. And so they have roughly the same distance. Like, you know, the iron has a slightly larger, the iron 2 plus ions have a slightly larger radius than the 3 plus ions, but we know they have the same number of energy levels. So really the best explanation is going to be based on the charge, and that's because the iron 3 plus charge will exert a greater force of attraction than the 2 plus charge. And it'll interact with the negative end of the water molecule to form an ion dipole interaction. Okay, so we have an unknown concentration of iron 2 plus. To determine the concentration, the student titrates the sample with permanganate ions, which converts iron 2 plus to iron 3 plus as represented in that equation. Write the balanced equation for the half reaction for the oxidation of Fe2 plus to Fe3 plus. So 2 plus to 3 plus, and it's oxidation, and so we know oxidation is losing electrons, and so the electrons must be on the product side, and that makes sense anyway to balance it out, but it only takes that 1 electron there to balance. Now in the actual overall reaction, you're going to have 5 of this happening, so you'll wind up with 5 electrons being transferred, but for just the half reaction, we just want to simplify it in the lowest terms. Now for part E, the student titrates 10 milliliter sample of the Fe2 plus, calculate the concentration. If it takes 17.48 milliliters, I'm going to change that to liters, and we've got 0.0350 molarity. Now remember that liters times molarity gives us moles, so when we multiply, we get 6.12 times 10 to the negative 4th moles of that MnO4 negative. And then we need to use a mole ratio. It's a 5-to-1 ratio there. So for every 1 MnO4 negative, there's 5 iron 2 plus ions formed. So if I multiply by 5, I'll get, I'll write it down here, 0.00306 moles of the Fe2 plus that must have reacted. And then we started with a 10 milliliter sample, or 0.01 liter sample. So if I divide, I get 0.306 molar Fe2 plus concentration. So make sure you use the stoichiometry of the reaction whenever you're figuring out equivalence point for titrations. So to deliver the 10 milliliter sample of the iron 2+ solution, the student has the choice of using one of the following pieces of glassware. Explain why the 25 milliliter volumetric flask would be a poor choice to use. Well, volumetric flasks only measure one specific volume. So in this particular one, it will be 25 milliliters. So we'll have a line, and that one line measures 25 milliliters. So it would not be good for measuring 10 milliliters because we don't know where that is in the flask. Beaker's also probably not a good choice, but it typically doesn't have very accurate graduations. But a burette or a graduated cylinder, depending on the precision, will probably be better choices. Now, in a different experiment, the student's given a sample of powdered iron that contains an impurity. The student uses a procedure to oxidize the iron to iron 2 oxide. The student collects the following data during the experiment. Calculate the numbers of moles of Fe and the FeO2 produced. Okay, so we need to use the Fe2O3 produced. A lot of people jumped, when this question was here, a lot of people jumped to using this one and changed grams to moles using the molar mass of iron. That's not a good choice because it's not just iron. There's also some kind of impurity in there that we don't know. So we need to use the Fe2O3. And so you would, 7.531 grams, you would first change grams to moles of the Fe2O3 using the molar mass, which is 159.7 grams per mole. And then I need to indicate, okay, so for every one Fe2O3, there are 2 iron atoms. So that way I can find out the specific moles of iron, and I would get 0.0943. We're using 4 sig figs? Yeah, so 0.09431 moles of just iron. And then for part H, we want to calculate the percent by mass of iron in the original sample. So now we want to use the moles of just the iron that we found, convert that to grams of just iron using the molar mass of iron, 55.85 grams of iron. And we get 5.267 grams of just iron. And then we can divide by the total mass of the original sample, the 6.724 grams, times 100 to find the percent by mass. And you get a 78.33%. That was iron. So like 22% is the impurity-ish. And then for part I, which is the last part for this question, if the oxidation of iron in the original sample was incomplete, so that some of the 7.531 grams of product was FeO instead of Fe2O3, would the calculated mass percent of iron in the original sample be higher, lower, or the same as the actual mass percent of the iron, and justify? So in this scenario, your mass percent would be lower. So because this formula here has only 1 iron for every compound, you can imagine here you would calculate, you'd plug in just 1 iron, and so you would have a smaller number of moles. Then in your second step, when you convert moles to grams, you would have a smaller number of grams, and therefore you calculate a lower percent by mass. That's a really good strategy for using for doing these sources of error kind of questions, where you just track, okay, where in the problem is that changing my calculation, and track that change throughout all of the subsequent calculations to figure out how it affects your final result. And don't forget to actually answer the question, say whether it's higher, lower, or the same, and then use your math to justify it. So now let's look at the first short free response question. So we have CS2 and COS, and in terms of the types and relative strengths of all the intermolecular forces, explain why the boiling point of CS2 is higher than COS. So this is one of those maybe doesn't follow the pattern type of questions, but we know that the CS2 has London dispersion forces, And no, that's probably not any dipole-dipole. It's pretty symmetrical there. Whereas COS has London dispersion forces and also some dipole-dipole. So the difference here, typically you would expect, because there's dipole-dipole, that the COS would have a higher boiling point, but it doesn't, okay? So that means its London dispersion forces in CS2 must be so much stronger that it's stronger than the London dispersion and dipole-dipole interactions in the COS. And now we need to explain why that is. Why is it so much stronger? When you're dealing with London dispersion forces, it always has to do with the number of electrons in the electron cloud. CS2 is larger and it has more electrons in that cloud, making it more polarizable. When it's more polarizable, it forms stronger London dispersion forces, giving it a higher boiling point. And then for part B, we have a 10-gram sample of CS2 is put in an evacuated 5-liter rigid container. It's sealed and heated, at which temperature it's all vaporized. What is the pressure in the container? So this is a Pivnert question. We need to change grams to moles. So first you would take the 10 grams of the CS2 and use the molar mass, which is 76.13, and find the moles of that. So 0.131 moles, and then we can use Pivnert. So the pressure is what we're looking for. Volume of the container is 5 liters. We have 0.131 moles. Our gas constant is 0.0821, and our temperature in Kelvin is 325. You just need to solve for pressure, multiply on the right side and then divide by 5, and you get the pressure is 0.70 atm. I'm sorry, I have to squeeze it in there. Now let's look at the second short free response. Remember, all of the short free response questions are 4 points total. Okay, so we have the weak acid HF in water, and then we have a certain concentration, and they give us a percent ionization is 13%. Two particulate representations are shown in figure 1 and figure 2. Water molecules are not shown. Explain why the representation of HF molecules in figure 1 is more accurate than the representation in figure 2. So HF is a weak acid. Okay, make sure you have your strong acids memorized, your strong bases memorized. Anything not on that list is weak. So HF is a weak acid. That means only some of them split apart into ions and react with water to form hydronium. So you'll see just some of them are changed into ions. This figure 2 has all of them in ions, which would be true if it was a strong acid, but it's not a strong acid. Okay, now for part B, we want to use the percent ionization data to calculate the value of Ka for HF. So you would take the 13%, and so 0.13, write that as a decimal, so, and then you multiply by the 0.0350 to give us the molarity that is ionized. So when you multiply that, you get 0.00455 molar. That's how much actually is ions. So that's, and because it's a 1-to-1, right, HF splits into one of these and one of these, we know that it's equal to the H3O plus concentration. And it's also equal to the F minus concentration. So now if we were to write an ice chart, which we should, I'm going to rearrange the reactants to make my ice chart a little neater. Because water is not included in our ice chart because it is a liquid. So HF, I have 0.035 of that to begin with and none of my ions. But we know that when it is ionized, it's 0.00455. And then, so the products are increasing, the reactants are decreasing. And because it's all 1-to-1-to-1, this decreases by x, this increases by x, this increases by x. And so we know that x is equal to that 0.00455. So I can subtract 0.035 minus the 0.00455, and I get 0.0305. I'm using 3 sig figs there. Now I can plug that into my Ka expression, which the expression is products over reactants, at equilibrium. And so Ka is equal to that of 0.00455 squared, because there's two of them, they're the same, and 0.0305. And when I solve for Ka, I get that it is 6.81 times 10 to the -4th when that is all solved. And that was a 2-point question. Anytime you have to do like more than 1 or 2 steps, it's definitely going to be a 2-point question. Now for C, if 50 milliliters of distilled water is added to 50 milliliters of the 0.035 molar HF, will the percent ionization in the solution increase, decrease, or remain the same? And justify your answer with an explanation or calculation. So you should not use Le Chatelier's principle for this, because adding water, just using that, you're not changing the concentration of water. It's a liquid. It's not aqueous, so that's not a good explanation. You want to use Q in your explanation here. If I'm adding 50 milliliters of distilled water to 50 milliliters of this, you're doubling the volume essentially. When you double the volume, you're having the concentrations of everything at equilibrium. So what that means is that for Q, you would do half of those concentrations, 0.00455 over 2 squared, and then the 0.0305 over 2, and solve for Q. And when you do solve for Q, you get, 3.39 times 10 to the -4th, which is essentially half the value of Ka. So Q is smaller than K at this point. When Q is smaller than K, right, that means that you don't have enough products. It will need to make more products to make Q larger to reach equilibrium. So the percent ionization will increase because you'll need to make more products to get the value of K to stay constant at that same temperature. So now let's look at question 6, the short for response. Okay, so a student sets up a galvanic cell. Remember, it's the same as voltaic cell. It has an electrode of silver immersed in 1 molar solution of silver and chromium immersed in 1 molar solution of chromium ions. Okay, the student measures the voltage and discovers that it's 0. Identify the missing component and explain its importance. The missing component, of course, is the salt bridge. The salt bridge will have ions, cations and anions, and they will balance the charge. So when one of those things loses an electron and passes it over to the other side, the charge isn't balanced anymore. So ions in the salt bridge will move from the salt bridge to whichever half reaction it needs to, or half cell it needs to, in order to keep those charges balanced and let the reaction keep happening. Now the student adds the missing component to the salt bridge and measures the cell potential to be positive 1.54. As the cell operates, the silver ions are reduced. Okay, so this one is reduced, so it stays exactly as it's written. Use this information in the information to do the following. Calculate the value of the cell potential for the reduction half reaction of the chromium. Okay, so essentially, when you flip this around and make it oxidation and add that to your reduction reaction, you'll get positive 1.54. So positive 0.8 plus something will give us positive 1.54. And when you solve that, you get 0.74. But that would be for when it's oxidized. This one is written as a reduction half reaction. So we need to flip that around to make it the negative 0.74 as it's written. So negative 0.74 as it's written. Now we want to write the balanced dynamic equation for the overall reaction that occurs. I'm going to write everything out here so you can see it. We have our reduction of the silver ions. We need to flip the chromium reaction because it will be oxidized. And then I need to make the electrons match. So I need to multiply the top reaction here by 3. That way the 3 electrons will cancel, and the electrons must cancel. So I have my 3 silver ions reacting with the solid chromium to form the chromium 3+ ions and the 3 solid silvers. That is my balanced net ionic equation. You should include states, but I don't believe they'll take off points for that. But it will help you understand what's going on a little bit better. Now, for part I calculate the value of delta G for the overall cell reaction. The equation that you need for this is delta G equals negative NFE. And so delta G is what we're looking for. N is the electrons involved in this process. So there's 3 electrons involved here. Faraday's constant 96,485, and our standard cell potential, they told us, was 1.54. So you just need to multiply, and it's asking for it in joules, which is great. So you get, when you multiply that, negative 4.46 times 10 to the 5th joules per mole. If you had written that out 0 like that, 446,000 joules per mole. So there is your delta G. Now remember that a negative delta G indicates a thermodynamically favorable reaction in the forward direction, which makes sense because we have a positive voltage for that voltaic cell. And now the last question on this test is your short period response, 4 points. Okay, so we have a complete photoelectron spectrum of an element. Identify the element. Okay, so we know that the one with the highest binding energy is always 1s. And so that makes this 2s and 2p. And the number of electrons, so s can only hold 2. So I know each of these lines represents 1 electron. So 1s2, 2s2, 2p3. 1s2, 2, you don't need to write it out, but I like to. So that means I have 7 electrons total, which means the element is nitrogen. You don't have to explain because it just says to identify. Now, a radioactive isotope of the element decays with a half-life of 10 minutes. Calculate the value of the rate constant K for radioactive decay and include units. Radioactive decay, you need to know, always follows first order kinetics. So that means we can use the first order half-life equation, which is 0.693 over K. And we can leave this in minutes. So 10 equals 0.693 over K. If you solve for K, you can get 0.069 as my value for K. And then the unit, because we're moving the minutes here to the bottom, it will be inverse minutes, minutes negative 1. You could change that to seconds and your answer would be inverse seconds, but you don't need to do that. And this one was actually 2 points, one for getting the correct value and one for getting the correct unit. You could also just remember that first order reactions always have just the time unit, whatever it is, to the negative 1 as the unit for the rate constant. Now for part C, we have 64 atoms of the radioactive isotope are originally present. What is the expected amount of time that will pass until only 1 atom of the isotope remains? Show how you arrived at your answer. I think the easiest way to do this is to just cut it in half, right? So 64, 32, 16, 8, 4, 2, 1. So it took 6 half-lives, 6 cuts to change it from 1, 2, 3, 4, 5, 6 to get it from 64 down to only 1. 6 half-lives. We know that each half-life is 10 minutes. So 10 minutes times those 6 half-lives gives you 60 minutes total. And that's it. You could have used the integrated rate law, but I think that is more complicated and not really worth it for this question. But you could use it. But make sure you're using the one for integrated rate law if you choose to do it that way. Half-life is a nice and easy way to do this because you're just literally cutting the sample in half, and each amount takes the same time for a first order reaction.